All right, that was our first question, our first type of problem. Let's move on to a very different kind of problem. This is a stochastic or problem, one driven by random chance, and in particular, a stochastic weather prediction problem. Again, the problem is written down on the screen, but I'll sort of summarize it very quickly. We have a series of descriptions of what the probability of the weather the next day will be given what the weather on a given day is. If it is sunny on a given day, there's a 50% chance it will be sunny again the next day. A 40% chance that the next day will be cloudy, and only a 10% chance that it will rain the next day. Weather patterns often persist. This doesn't seem unreasonable. If it is cloudy one day, there's a 50% chance it will still be cloudy the next day, and a 25% chance each of either being rainy or sunny the next day. If it is raining, there's a 40% chance it will still be raining the next day, a 40% chance it will be cloudy but not raining, and a 20% chance that it will be sunny. So this is describing what we know about the sort of ability to predict weather the next day based on what we know the current day somewhere in some hypothetical location. We then might ask different sorts of questions if we have this kind of information. We might ask, if it is sunny on Wednesday, what is the probability that it will rain on Sunday? Maybe it's Wednesday and you're thinking of inviting people over for a barbecue. A well socially distanced barbecue. Is it likely to be raining, or is it likely to be sunny? What are those probabilities? We could also pose the question, is with this information, what's the probability that it's sunny on any given day? If we don't know anything about sort of what day of the year it is, we're just going to pull out a random day. What's the probability that it's sunny based on this information? Can we answer these questions? How would we answer these questions? Once again, we're going to take a systematic approach, formulate the model, think about what we're trying to find, and then ask, how might we get that answer? This is a class of problem known as a Markov chain, where the key variables are actually probabilities that the so-called system, this is different than a system of equations, but the physical system that we're dealing with, the weather in this case, the variables are the probabilities that the system is in a particular state at a particular point in time. Right? These kinds of stochastic processes, Markov processes, are often most easily understood by writing a schematic, kind of a cartoon that shows what the possible states are and what are the probabilities of moving from one state to another in a given step. This cartoon here, schematic here, summarizes the information for this particular system. We have 3 different possible states for the weather. It can be sunny, it can be cloudy, or it can be raining. If it is sunny on one day, there's a 50% chance that it stays sunny. We represent this by an arrow going back from sunny to itself, labeled 50%. There's a 40% chance that if it's sunny, it becomes cloudy. So we have an arrow from sunny to cloudy with 40%, and a 10% chance that if it's sunny, it becomes rainy. we have the arrow from sunny to raining with 10%. We do the same for the transitions from each of the other states. If it starts off as cloudy, there's a 50% chance that the next day is also cloudy. There's a 25% chance that it becomes raining. There's a 25% chance that it's sunny. 3 arrows out of cloudy to the 3 other states. If it's raining, there's a 40% chance that it's raining the next day, a 40% chance that it's cloudy the next day, and a 20% chance that it's sunny the next day. One thing that you will note is that if you add up the probabilities for all of the arrows out of one state, it has to be 100%. If it's sunny today, there's a 100% chance that tomorrow will have weather. And so if we add up all of the different possible weather scenarios, we have to get 100%. And we see 50 plus 40 plus 10 is 100, 50 plus 25 plus 25 is 100, 40 plus 40 plus 20 is 100. Another way of summarizing this information is in a transition table, where we have, we write out a table where the columns and the rows are both the set of possible states: sunny, cloudy, rainy, sunny, cloudy, rainy. The columns correspond to the weather on the current day, or the day in question, and the rows correspond to the probability on the next day. And then we really just fill in this table based on the information in this. If it was sunny, there's a 50% chance that it will become sunny. If it was sunny, there's a 40% chance it will become cloudy. If it was sunny, there's a 10% chance that it will become rainy. This column corresponding to the all of the ways that we can end up in after being sunny in a certain day add up to 100. We do the same thing for cloudy. If it was cloudy, there's a 25% chance that it's sunny, a 50% chance that it's cloudy, 25% chance it's rainy. They add to 100. If we start with rain, 20% sunny, 20%, 40% cloudy, 40% raining, sum to 100. This summarizes all of the information in the problem, but it's not a mathematical model in the sense that we really think about it yet. This is a kind of a model, but it's not a set of equations that we know how to work with. So let's try to now formulate the set of equations we would need. We're going to work with the schematic rather than the text, just because the schematic is a much, at least in my opinion, easier way to think about the problem. We start off by defining the variables. The variables are the probability of being sunny, cloudy, or rainy. And we have to highlight on a particular day. So this is going to have variables that actually, I'm going to use P for the symbol for the probability. I'm going to use a subscript S, C, and R to correspond to sunny, cloudy, and rainy, and another subscript that says what day are we on. And use I as a counter of the days. Then we're going to now write down our equations. How do we summarize all of these equations? Well, we need one equation for each weather state. And what we're going to really want each equation to tell us is what is the probability that it's either sunny the next day, cloudy the next day, or rainy the next day. We write this down as the probability sunny I plus 1 if we knew that I was the original day. And the way that we get this probability is by adding up the possible ways that we can get there. So how can we be sunny if the next day? Right? There's 3 ways that we could get to being sunny on a particular day. It could have been sunny the day before and still sunny. It could have been cloudy the day before and then sunny. It could have been raining the day before and then sunny. The probability that it was sunny, cloudy, or rainy the day before are these PSI, PCI, and PRI. And each of these probabilities has to be multiplied by the probability that if it was sunny, it stays sunny. If it was cloudy, it becomes sunny. If it was raining, it becomes sunny. And that's what is highlighted here. So the probability that it's sunny the next day is the probability that it was sunny the day before, or sunny the current day, I should say, multiplied by a 50% chance that it stays sunny, plus the probability that it's cloudy the current day, multiplied by a 25% chance that it becomes sunny, plus the probability that it was raining, multiplied by 20% chance that it becomes sunny after raining. If we look at the coefficients in this equation, these essentially correspond to the entries from one row of this table. The probability that the next day will be sunny, the probability the next day will be sunny is a sum over contributions from each of the entries in this row. The same thing is done for the cloudy the next day. The probability of being sunny multiplied by 40%, the probability of being cloudy by 50%, the probability of currently being rainy by 40%. And the same thing for the last entry, 10% times the probability of being sunny, 25% times the probability of being cloudy, 40% times the probability of being rainy. We now have a mathematical model written as a set of equations that give us the probabilities on the next day in terms of the probabilities on the current day. All right, we have our model. How do we work with this model? We have two different problems we've imposed. Let's think about each of them individually. The first, if it is sunny on Wednesday, what is the probability that it will be raining on Sunday? So what we really want is we need to sort of assign numbers I to these various days. Let's set the number 0 to be equal to Wednesday. If it is sunny on Wednesday, that means the probability S0, the probability is sunny on day 0 equals 1, 100% chance. And there's a 0% chance that on day 0, on Wednesday, it's cloudy or rainy, because we know it's Sunday. And we want to know the probability that it's raining on Sunday. Well, if Wednesday is 0, then Thursday is 1, Friday is 2, Saturday is 3, and Sunday is 4. So what we want to know is what is PR4, the probability that is raining 4 days later, if we know that on day 0, the probability of being sunny was 100%. How can we find this? Really, the only way to find this is by taking an iterative solution. Our system of equations tells us how to find the next day probabilities given the current day probabilities. So we can start with day 0 and find the probabilities on day 1, then use the probabilities on day 1 to find those on day 2, use those on day 2 to find those on day 3, use the ones on day 3 to find those on day 4, and that will give us our answer. Let's try to do this. Wednesday. probability that it's sunny is 1, cloudy and rainy are 0. Okay. These were our equations that we're going to use to do the update. How do we find the probabilities on Thursday? We plug these numbers in. PS 1 would be 0.5 times 1 plus 0 plus 0, or 0.5. The probability of being cloudy on day 1 would be 0.4 times 1 plus 0 plus 0, or 0.4. The probability of being rainy on day 1 would be 0.1 times 1 plus 0 plus 0, or 0.1. First, day 0 is given. Day 1 is very easy to calculate. The next days start getting a little bit messier because now we have to start multiplying these sort of decimals to get our probabilities. For Friday, day 2, the probability that it's sunny is 0.5 multiplied by 0.5, which is 0.25, plus 0.25 times 0.4, which is 0.1, plus 0.2 times 0.1, which is 0.02. Adding these up gives us 0.37. Similarly, for cloudiness, 0.4 times 0.5 is 0.2, 0.5 times 0.4 is 0.2, 0.4 times 0.1 is 0.04, 0.44. Rainy on Friday, rainy on day 2, 0.1 times 0.5 plus 0.25 plus 0.4 plus 0.4 times 0.1 is 0.05 plus 0.1 plus 0.04, or 0.19. Always good in these scenarios to double check at each step that your probabilities add to 1. Starting point, we had a probability of 1 being sunny and 0, 0. For the others, it's 1. For the first day, 0.5 plus 0.4 plus 0.1 is 1. These have to add to 1 because, again, the probability that there is some weather is always 100%. Right? Double checking our numbers for day 2 or for Friday, 0.37 plus 0.44 is 0.81 plus 0.19 is indeed 1. Everything is consistent there. We now do the same thing for Saturday using these numbers, the Friday days as the input. Day 3, probability of sunny is 0.5 times 0.37 plus 0.25 times 0.44 plus 0.2 times 0.37, which ends up being this value here, 0.03033. Sorry, not 0.2 times 0.7, 0.2 times 0.19. For the cloudy, it's 0.4 times 0.37, 0.5 times 0.44, 0.4 times 0.19. That gives us 0.444. And for the rainy on day 3, we have 0.1 times 0.37, 0.025 times 0.044, 0.4 times 0.19, which gives us 0.223. If you add these up, we do indeed get 1 again. Everything works out well. This is getting tedious. I do not recommend that you do this without a calculator. I actually double-checked my work on this using MATLAB to make sure that I was getting everything right. This kind of a problem can be tedious, right, and prone to error. We're now ready to look at the last problem. The last step. For Sunday, we can actually skip a little bit of work because the only thing we care about is being rainy. And so I'm not going to bother calculating the probability of being sunny or cloudy. I'm only going to calculate the probability of being rainy, which is 0.1. Now using the Saturday or day 3 numbers, 0.1 times 0.333 plus 0.25 times 0.444 plus 0.4 times 0.223 gives us 0.2335. We have an answer, a mathematical answer. We now need to go and put this back into the context of the problem, and we can say that if it is sunny on Wednesday, there's a 23.35% probability it will be rainy on Sunday. We could get an answer, but it was tedious and very easy to make mistakes, especially if you were trying to do it without a calculator. What about the second problem? What is the probability that it will be sunny on a randomly selected day of the year? What does this really mean? Well, we can think about it 2 ways. One way is, well, a randomly selected day of the year, we should lose any information about where we started. Because we don't know anything. We're just saying we randomly picked a day. That means we don't know how far away we were from a day that we knew the weather. That suggests one approach of finding this answer, which is to, in some sense, find the limit as I goes to infinity of the probability of being sunny, starting really almost anywhere. We could start at the being sunny on a given day, as we did for the first. And then try an iterative solution and ask, maybe, perhaps, if we keep trying and trying, we'll find an answer. We'll find the answer doesn't change anymore. And that might be one way to get to the solution. Another way, we might say, what does it mean to really have the probability on a random day? Well, random days are exactly that. We don't know where they are. And the probability of any randomly selected day should be the same. And probability of being sunny on any randomly selected day should be the same. So perhaps we can phrase this as, how do we find a set of probabilities such that the probabilities on one day are exactly the same as the probabilities on the next day? This is what we might call an equilibrium distribution. A distribution that if we are in these probabilities, it doesn't change anymore. And that's a second way to solve that problem. I'm not the iterative solution, where you're trying to find the limit of as we go to infinity, is not something I ever recommend trying to do by hand. I implemented this computationally using MATLAB and ran a number of simulations, ran a number of iterations up to 100, and kind of from there sort of try to figure out exactly when you were getting converged. And it turns out that actually we've complete the day 4 numbers. We already had the day 1, 2, and 3 numbers from this starting state. Day 5 looks actually very similar to day 4, but it is still changing. Day 6, again, looks similar to day 5, but still changing a bit. Day 7, day 8. By the time you go to day 9, the answer isn't changing to within 4 significant figures. And if you run this out 100 or 1,000 steps, I'm not showing the higher numbers, you still get that same number to 4 significant figures. That's pretty strong indication that this is in fact the equilibrium distribution. The limit as we go to infinity of the probability of being sunny is 0.3175. We can also do this in that other approach that I sort of suggested. We can ask, when are the next day probabilities, the right-hand side here, exactly equal to the left-hand side? We do that by replacing the I plus 1s by i's on this side. I then can move these, this part of the problem over to the other side, basically subtracting all of these terms from the left-hand side, leaving 0 on the right-hand side. And this gives a system of equations. 1 minus 0.5 is 0.5, minus 0.25 minus 0.2 for these three terms. Minus 0.4 PS, 1 minus 0.5 is plus 0.5 CI, minus 0.4 PR, second piece, minus 0.1 PS, minus 0.25 PC, 1 minus 0.4 is plus 0.6 PR. This is now a system of equations that we could try to solve. It's not necessarily a trivial one too, but we can try the same kind of tricks that we have tried before. One way we can do that is by, say, doing the same kind of subtractions and additions of equations that we've done before. In this case, if we take a look at equation 2 and equation 1, the middle term differ by a factor of -2. So if I add 2 times the first equation to the second equation, it'll make this PC term disappear, right? So negative 0.4 plus 2 times 0.5 is 0.6 PS, plus 0.5 plus 2 times negative 0.25 is 0. That piece disappears. Negative 0.4 plus 2 times negative 0.2 is negative 0.8 PR. 0 plus 2 times 0 is still 0, so the right-hand side remains 0. This is our equation that we get from that manipulation, 0.6 PS minus 0.8 PR. This lets us write PR in terms of PS. PR is 0.6 over 0.8 PS, or 0.75 PS. Once we've done this, we can then substitute in all these PR values for 0.75 PS, and that gives us a new system of equations where the first column and the second column are exactly the same, and this last column is now in terms of PS instead of PR. We then combine this column with the first because they're both in terms of PS, and now we have equations that only have 2 unknowns. We can then do some addition and subtracting of equations to try to get rid of them and see what we have. Actually, we might note, looking at this, that the first and last equations after we have done this manipulation are in fact exactly the same. The second equation is just negative 2 times those values. All three of these equations are simply multiples of one another. Which means that if we try to do any subtractions or additions of these rows, we're actually just going to end up having 0 equals 0, which isn't going to give us any more information. But we can take this single equation we have and rearrange it. Rearrange it to give PC in terms of PS, the probability of being cloudy in terms of the probability of being sunny. And we get this relationship here of PC is 1.4 PS. You might think that now we don't know anything more we can do. We're kind of stuck. We weren't able to get a single answer for the probabilities. But remember, we have another piece of information. And this is something that's always important to remember with these kind of Markov chain problems. There's an extra piece of information sitting in the fact that these are probabilities. They need to add to 1. So the extra piece of information we have is that PS plus PC plus PR has to equal 1. We have PR in terms of PS. We can plug that in here. PC in terms of PS, we plug that in here. This gives us now, a well-defined expression, 3.15 PS equals 1, or PS is 1 over 3.15. Plug this in your calculator, you will find that this is exactly the same number as we got with the iterative approach. It's nice to see that we get that. 2 ways of getting an answer, both of them a bit messy, probably not obvious that that's for most of you, that that's how we should get the answer. As we move through the semester, we will find more robust, we will learn more sort of consistently how to approach this kind of problem. Again, always move back to the original problem, phrasing our mathematical answer in the original language. There is a 31.75% chance of a probability of it being sunny on a randomly selected day of the year.